So today I want to talk about the price equation. The price equation is a really important formalism used in evolutionary biology, population biology, and it talks about how a trait can change from one generation to the next, from the parental generation to the descendant generation. And it basically partitions out how change happens across a generation according to either selection or other types of transmission that are related to population structure. And um, it's a simple, pretty elegant equation that is used a lot in cultural evolution. Um, and it's a very general formulation that allows you to talk about basically anything where there's change from an origin to a descendant group. And this does not need to be reproduction. This can be, for example, cultural change. And we're gonna talk about that later in the quarter. So I'm gonna share my screen, and what I want to do is basically show you how it's derived. Right? You see it. It looks a little mysterious. It's kind of a funny looking little formula. But its derivation is pretty straightforward. It's some algebra, and you have to know your definitions of expectation and covariance in particular. And unlike other videos, I'm actually starting not with a blank screen. It's really tedious to write down all of these definitions. So let's just go through them. And I'll make this red. And so we're going to start by defining z sub I as the trait with label I in the parental generation. Okay, and every time we talk about the parental generation, it'll just be z sub I or q sub I or whatever. And every time we talk about the descendant or the offspring generation, we're going to put a prime on it. Okay, so z prime sub I is the trait with label I in the offspring generation or the descendant generation. Okay, and z prime sub I is just the value of z sub I in the parental generation plus the change in z sub I, right? It's very straightforward. All right, now we're interested in fitness, and so we want to know about the relative frequency of these different types in the population. Things that have higher frequency have higher fitness, right, over time. So we will define q sub I as the frequency of label I in the parental generation, and similarly, we'll define q prime sub I as the frequency of the label in the offspring generation. Now, here's a really important, both conceptually and mechanistically important definition. The frequency in the descendant generation of label I, right, is going to be a function of the fitness of label I, right, times their frequency in the previous generation, right? And then we always normalize by mean fitness. Some people, when they derive the price equation, they'll set mean fitness, they'll set W bar equal to 1. We're not going to do that. It's just better to remember that you have to normalize by mean fitness. But just think about this for a second. And I should point out that W is fitness. This is a funny convention from population genetics, and we're going to keep it here. That your frequency in the descendant generation, right, is just the frequency that you had in the parental generation times your relative representation, right, your relative fitness, how much you increase or decrease, or for that matter, stay the same across the generations. So that's really important. And we can also define a delta QI, right, as the change from in our descendant generation minus our parental generation. So it's just the change that happens across the generations. And using this definition of Q prime sub I, right, we can derive out this relationship for delta QI, and that also becomes useful, right? So The algebra is pretty straightforward. We just substitute q prime of I. We substitute for that qi wi over w bar, right, which is just this definition right here, minus qi. We take the qi's out, and what we're left with is qi times the relative fitness minus 1. Okay, so those are our definitions. From there, it's a pretty straightforward thing. There's quite a bit of algebra, right? It's a little hairy, but the good news is that I've worked through it all for you. And what we are interested in is the change in the mean of this trait. Okay, so we indicate the mean by putting a bar over z. So the change in z bar is going to be, you can write it as delta z bar, and it's just going to be, as with our previous definitions of these deltas, right, that it's just z bar prime minus sub I. Oh, no, not sub I. Sorry, this is the overall. So we're summing across, we're going to take the average across all the i's. So it's z bar prime minus z bar, okay? And this is where the expectations come in. What is z bar prime? Well, it's going to be the sum across I, but I'm going to not write the I because it just makes everything look even messier. So just remember that all of these sums are across all the I values. Q prime I, z prime I, but not that, sorry, that, z prime I, okay? That's just the formula for an expectation, right? The frequencies, right? And sum up all the frequencies and they equal to 1, right? So it's a probability mass function. And then the values, okay? We sum those across all possible I and we get an average. And we get the exact same thing, or parallel thing, Q sub I, Z sub I for the parental generation, okay? Good. Now, let's do some algebra, shall we? The first thing we're going to do is basically we're gonna use a little algebraic trick. So here's what we're gonna do. We're gonna change this first sum, Q prime I times Z prime I minus ZI. You see what we did there? We basically just are subtracting a ZI here in our sum. And we can do that, right? We can do that as long as we do the following, plus sigma Q prime I ZI, okay? So that means that our equation is still correct, right? We've just used a little algebraic trick that will come in handy because it helps us figure out some identities in here. And then of course we have to subtract this part as well. Still, QI, ZI. All right. So let's see. So what can we say about this? Let's change the pen color for a second. The first thing that I want to point out is what is Z prime I minus ZI? Well, that's just delta ZI, right? Okay. And then the second thing, let me see. Did I write in my notes? We've already dealt with that, right? That we have to add this in order to account for the fact that we're subtracting ZI from our Z prime of I. Okay. So now we can actually just rewrite this. And this is important too, right? This is good. Notice that we have also this sum that has a Q prime of I, right? And this sum that has and we're averaging Z of I using Q prime of I as our frequencies. And here we're averaging Z of I. Here, you can't see it when I point at it. Here we're averaging Z of I. Here we're averaging Z of I with the frequencies of Q of I. And so what's Q prime of I minus Q of I? It's just delta Q of I, okay? So we can then rewrite this right side of our equation, sigma q prime of I times delta z of I plus the sum of delta qi times zi. And just for reference's sake, I'm going to call this one A, and I'm going to call this sum B, and we're going to do some more algebra. We're going to work out what sums A and B are in ways that are more useful for us, okay? So give me 1 second. Let's start with sum A. So let's rewrite it, sigma q prime of I times delta z of I. Okay. Right. And so the first thing we can do is note, that's not the right code. That's the right code. That this, we did this on the first page, right? This is just qi times wi, right? That the frequency in the descendant generation is just the frequency in the parental generation times its relative fitness. Okay. So let's rewrite it that way. So we'll say the sum of qi wi over w bar times delta z sub I. Okay, so we're just summing the changes of the zi's, right, across generations. Now, let's look at here. What do we have here? When we have a sum and some probability measure, right, some frequency measure of the different types, what do we have? We have an expectation, okay? That's, we're taking, this tells us the sum across qi, right, tells us that we are taking the average, the expectation of the second term, wi over w bar times delta zi. Okay, so we can actually write this down now simply as the expectation of w delta z divided by w bar. Right, because the average of an average is just that number again, right? So the average of w bar is just w bar. And what we've got here is we're taking the average of, we've got the average of our w's times our z's. All right, so that is the first term. That is it for the price equation. That's sum A. Now let's move on to sum B. Okay, this one is a little more involved. So we'll write it down, sigma delta qi z sub I. All right, and we will remember, once again, I'll just write it down here so that we're perfectly clear about this, that delta qi is equal to q prime of I minus q of I from the first page, and that after doing just a little bit of algebra, this is equal to qi times wi over w bar minus 1. If you need to be reminded how we get from the delta qi to this, just go back to the beginning of the video, the first page of the notes, okay? So let's write it out that way. Hopefully I left enough space here. The sum of qi wi over w bar minus 1 times zi. Okay? What I'm going to do now is another one of these algebraic tricks. You see that we've got this w bar in the denominator here, I'm actually going to bring that out. And remember, it's just a number. There's no index on it, right? It's just the average fitness. So we can bring it outside the sum. And what I'm going to do is do 1 over W bar times the sum QI times, obviously, taking out the W bar makes this just WI. What does the 1 make it? Well, it makes it W bar, right? We divide W bar by W bar, and we have a 1, and we had a 1 here. So that's algebraically equivalent times Z sub I. And I'll draw your attention to the fact that we have another expectation here, right? We're summing over some frequency. And just, you know, to be maximally pedantic, what I'm going to do is just point out what exactly it is that we're summing over. What is our expectation about? QI. Let's multiply the Z sub i's through here. Okay, so what we have is WI ZI minus W bar ZI. And the question is, so it's an expectation. It's an expectation of this this thing in parentheses here, okay? And do we know what that is? We actually do. It's from the notes on expectations, variance, and covariance, right? It actually has the form. So this whole thing has the form of WZ minus, right? It has the form of the average of the product minus the product of the averages. Okay, and what is that? That's a covariance. Okay, so this whole term here is just the covariance between W and Z. That's pretty cool. And then we can't forget that we had mean fitness out in front, so we have to divide by mean fitness. All right, we're getting really close. We've basically done it all. We just need to assemble it. So let's put a big fancy header, the price equation. Remember, what we care about is delta Z. We're interested in the change in the trait from one generation to the next. It's equal to, and I'm actually going to flip these two around. I'm going to put sum B first, the covariance of W and Z divided by W bar, plus the expectation of W delta Z divided by W bar. And then what we'll do is we'll multiply everybody through by W bar, and we'll get the form that you typically see in the literature, textbooks, and that sort of thing. And there we go. That is the price equation. Okay, it's pretty cool. I'm going to basically stop with the algebra and not talk at all in this video about what this means. That's pretty important. It's probably not at all obvious what this means, but it's already pretty long, and this is really about the derivation. We'll talk about this more, but I will just draw your attention to there are two terms, and we can think of this one, the covariance, as representing selection. It's the selection term of the price equation. And the second one being transmission. The change from one generation to the next is a result of the transmission from one generation to the next, plus the effect of selection. Seems pretty commonsensical, but this is a really neat way to prove it, and it turns out to be very useful in an applied way, in part because of many of the relationships between covariances and expectations. Um, it's a really amazingly productive idea and equation. And we'll see what we can do with it. Um, uh, it'll be interesting, and it's not something that's been used a lot in the climate change adaptation literature, but this is a really important model of behavior change in cultural evolutionary studies, and we're gonna approach it like that. All right, so that's all for the price equation for now. I will see you in class, or see you in the next video, or you'll see me in the next video, whatever. It's kind of awkward how to end these. All right, bye.